Hi everyone, welcome to the programming platform. My name is Arjit Nath, and in this video, I'll be going through the Singleton Design Pattern. In today's topic, we'll first discuss what is Singleton Design Pattern, and then how to make a class Singleton. Then we'll go through all the various types of Singleton initializations. At the end, we will see what are the various ways in which the Singleton pattern can be violated, and we'll also see how to overcome those violations. So let's get started. The first question we should ask is what is Singleton Design Pattern? Singleton Design Pattern is one of the creational design patterns. Creational design patterns are generally concerned about object creation mechanism, trying to create objects in a manner that is suitable for a given situation. What Singleton Design Pattern achieves is that it ensures only one instance of a class will be available in JVM. To make sure the instance is accessible, it provides a global access point for the instance variable. Singleton instances are used in applications or frameworks where only one instance is required to invoke its business logic throughout the application. Like a database connection can have a single instance that can call it from anywhere in an application. This brings us to the question, how to make a class singleton? There are three basic steps which we need to follow to make a class singleton. First, to make a singleton class, we should not allow an external source to create an instance of the class using the new operator. That will defeat the very purpose of singleton. To do this, we will make the constructor of the class as private. In this way, we can stop any external class from creating an object of the singleton class. Then we have to have a private static variable of the singleton class type that will hold the instance of the class being created. We are making this instant variable as private and not as public or protected because we want this variable to be accessible only from a global access point. Last of all, we need to have a public static method that returns an instance of the singleton class type. This method will serve as a global access point for the previously mentioned instance variable. We choose this method to be public as we need this to be freely accessible from outside of the singleton class. Also, we need this method to be static as this method should be directly accessible without instantiating the class. There are various ways in which we can initialize a singleton class, like eager initialization, lazy initialization, synchronized initialization, and others. We will go through each and every type of singleton initialization along with its advantages and disadvantages. First, let's get started with eager initialization. In eager singleton initialization, we create a singleton instance in a static initializer. This ensures that the singleton class instance is loaded up during the class load itself. Since the static initializer is only invoked for the first time when a class is loaded, it guarantees that only one instance will be available for that class, even when multiple threads are acting on it. Thus, it provides complete thread safety. Let's go to the code to understand how the eager initialization is done. Here in line number 4, you can see that we have created a private static final instance of this eager initialization class. The static ensures that the instance is created during class load itself. The final ensures that the instance cannot be modified going forward, and the private ensures that it cannot be accessed directly from outside without an access point. As previously mentioned, we have also created a private constructor such that an object of this class cannot be created from an external source with the new keyword. Finally, we have created a public static getInstance method which directly returns an instance of the eager initialization singleton class. The public ensures that this access point will serve as a global access point, and the static ensures that we do not have to create a class instance to access this method. We can directly access this method with the class name itself. Here in the main method, we are calling the executeEager method. In the executeEager method, we are trying to understand whether multiple calls to the eager initialization.getInstance method will return you different object instances or not. On executing, we find out that it is always returning the same object instance. No matter how many times you run this program, it will always return you the same object instance again and again. Also, as I mentioned earlier, the eager initialization provides complete thread safety. For that reason, we have created a new method called executeEagerThreads. Inside this method, we have created an executor service of new fixed thread pool type, which contains two threads. And we are passing the eager initialization.getInstance method call inside both the threads, and we are printing what is the outcome of this particular getInstance method call. We are trying to understand whether passing this eager initialization.getInstance method in two threads at the very same time will produce the same expected output or not. Let's try to execute this method and see what is the outcome. We see that both the threads are returning the same object instance. And no matter how many times we run this, we will see that it will always return the same object instance. So this proves that eager initialization is completely thread safe. Now we'll look at some of the drawbacks of this kind of initialization. For eager initialization, one of its positives is its biggest drawback. The term eager in eager initialization means that the singleton instance is created during class load, even before it is required or requested. It may happen that the singleton object is very big. Thus, creating it during class load can be a very expensive operation. Also, there are no guarantees that this singleton object will be ever required in the business logic. That is why it is always preferred that we create the object when it is required to make the application start smooth and fast. This brings us to our next type of initialization called the lazy initialization. Now we'll look into lazy singleton initialization. The main disadvantage of eager initialization is addressed in lazy initialization technique. In lazy initialization, rather than creating the singleton instance as a static initializer, as we have seen in eager initialization, we will do that inside the getInstance method. For the same reason, we do not have the instance variable as final in lazy initialization, since we do not want the instance to be initialized during class load. Here, the instance is created in the static getInstance method. Every time the getInstance method is called, it checks if the instance variable is null or not. For the first invocation, it will be null. Then it creates the instance of the singleton class and initializes in the variable and returns it. From second invocation onwards, since the instance variable is no longer null, it returns the instance variable directly without performing any operation. Thus, the instance of the singleton class is created only when called upon and not during class load. This is a major advantage of lazy initialization over eager. Now let's come to the code of lazy initialization technique. In the lazy initialization class, the first thing that we are doing is creating an instance variable of lazy initialization type. We are creating the instance variable as a private static variable called instance underscore lazy. We are also creating a private constructor. Inside the getInstance method, we are first checking if the instance variable is null or not. For the very first invocation, the instance variable will always be null. So it will go ahead and create a new object of the lazy initialization type and initialize it inside instance underscore lazy, and it will return the same. From next invocation onwards, this variable will always have a value, so it will never be null. So it will return whatever object was initialized during the first invocation. And that is how lazy initialization is working. So the term lazy basically means that the object will get created whenever required. So the object is getting created over here only when we are calling the getInstance method. One point to note over here is even though we are creating the constructor as private, we can still call this constructor from anywhere inside this class. Basically, a private constructor means that this constructor cannot be called from outside of this class. That means that anyone from outside of this class cannot create an object of this class. The first thing that we will try to test is whether the lazy initialization technique is properly upholding the singleton principle. For that, we have created a method called executeLazy, and inside this method, we are calling the lazy initialization.getInstance method twice and printing the outcome. Let's see how it goes. If you see over here, both the calls to the lazy initialization.getInstance method are returning the same object. And no matter how many times you execute it, it will always return the same object. So that means in a single threaded environment, the lazy initialization is working properly. Now, we will try to understand how this lazy initialization technique is working internally. For that, we will put a debug point over here in line number 9 and start this main method in debug mode. Let's see how it goes. If you see over here, during the first call to the lazy initialization.getInstance method, the instance underscore lazy variable is currently null. So if I proceed forward, you will see it will go inside the if block and it will create the lazy initialization object. Once it is created, the lazy initialization is initialized with the object variable and it will return the object to the first call of lazy initialization.getInstance. During the next call, it will again go ahead and check whether this instance variable is null or not. But this time, it is no longer null. It has a value that was initialized during the first call. So it will not even go inside the if block. It will directly return whatever was previously created and it will go out. So when you print both the objects, lazy object 1 and lazy object 2, you will see that both the objects are same because the object has been created the first time. The second time it is only returning the same object. Even though lazy singleton initialization works well in single-threaded environment, the main drawback of this approach is that it is not thread safe. If multiple threads are calling the singleton instance at the same time, then more often than not, it will return different objects for both the invocations. So this directly violates the singleton principle. To test this theory, we have created a method called execute lazy thread. Inside this method, we have defined an executor service with two fixed threads. And inside the executor service, we are trying to submit two threads inside which we are calling the lazy initialization.getInstance method and printing the outcome. Let's see how it goes. I will uncomment this and comment this one and I will execute the main method. You will see over here that for both the thread invocation, it is returning two separate objects. If I run it again, you will see it is again returning two separate objects. So this means that lazy initialization does not work in multi-threaded environment. Now let's get started with synchronized singleton initialization. What we learned in lazy initialization was that it is not thread safe. So the first thing we should do to add thread safety is to wrap the singleton object creation logic with a synchronized block. Now even though this approach may look thread safe, logically this approach is not thread safe at all. Let's go to the code to see why that is. There are multiple ways in which we can try to apply thread safety to our singleton class using synchronization. We will start with a very basic way of using synchronized keyword on the method level with lazy initialization. When I say method level, we'll add a synchronized keyword in the getInstance method level and let's see how it works in a multi-threaded environment. Over here, we'll execute the execute lazy thread method where we are using the executor service to add the lazy initialization.getInstance method call in two threads. And let's see how it goes. If you see over here, both the threads are printing the same object when we are adding synchronized keyword. And how many times, no matter how many times we execute the code, it will always return the same object. That means adding the synchronized code on a method level is working fine. But the major problem with this technique is the technique itself. Synchronizing an entire method can cost heavy as multiple threads can request for the singleton object using the getInstance method at the same time, but only one thread will get it. Say there are 10 threads who is trying to access this getInstance method, but since we have put synchronize on a method level, only one thread will get access to this method, whereas all the other 9 threads will stay in the waiting state until and unless that thread releases the monitor. So that is not a very good practice to have. One way to improve this logic is rather than having a synchronized keyword on a method level, we can only keep the object creation logic inside a synchronized block. Let me open the code to show you how that will be done. You can see over here, we are keeping only the object creation logic inside the synchronized block. Even though this is making the code much more efficient, but this method is no longer thread safe. I'll tell you why. Let's say there are 10 threads trying to access the getInstance method of the synchronized initialization class. Now, when all the threads are calling this getInstance method, they will first check whether the instance underscore synchronized instance variable is null or not. All the threads will find this variable as null because this variable has not yet been initialized with an object. All the threads will come to line number 10, where only one thread will get access to this monitor, whereas all the other 9 threads will have to wait at line number 10 till the first thread completes its execution and release the lock. When the first thread creates an object of synchronized initialization class and initializes it to this variable, it will go ahead and return that particular value. Now, since all the other threads are waiting at line number 10, they will no longer check if the instance underscore synchronized variable is null or not. What they will do is all the other 9 threads will one by one go ahead and create their own synchronized initialization object, initialize it to the instance underscore synchronization variable, and return it. That is why this particular logic fails in a multi-threaded environment, and every thread that is calling this particular method at the same time will return different object value. Let's go to the main method and see how this synchronized initialization class behaves in a multi-threaded environment. In the main method, we are creating an executor service again with 2 threads and printing the objects that are being returned by synchronized initialization.getInstance method in each of the threads. Let's run this. If we run it, we'll see that both the objects are returning different values. And no matter how many times we run it, it will most of the time return different values. So this proves that having a synchronized block does not solve the thread problem. Now let's have a look into double check lock singleton initialization. Double check locking technique is an efficient upgrade to the synchronization instantiation of singleton class. Here, we will add one more level of null check for the instance variable just after obtaining the lock with the synchronized block. Let's go into the code to check how it works. This is a class to understand double check locking initialization. The code is very similar to synchronized initialization with a minor difference. Here, in the getInstance method, you will see that at first we are checking whether the instance is null or not. If the instance is null, we are allowing any thread coming into this method to acquire the lock on the object creation logic. But before that, we are again checking whether the object initialization variable is null or not. If you remember, the main point of failure for synchronized initialization was that all the threads are waiting for the lock after the null check. So whenever one thread is releasing the lock and the other is acquiring it, it is directly going ahead and creating another singleton object without checking whether the previous thread has already created the object or not. This issue is resolved by double check locking, wherein every thread who is acquiring the monitor is checking both before and after acquiring the lock if any previous threads has already created the singleton instance. If yes, then it is directly returning the created instance, or else it is creating a new instance and then returning it. Let's execute this code and see how it performs. We will go to the main method and execute this code. In the main method, we are calling 2 threads and performing the same operation that we have been doing for the previous examples. Let's run the main method. If you see, both the threads are returning the same instance. And no matter how many times I execute, both the threads will always return the same instance. So this let us believe that double check locking is a very good way in providing thread safety. Let's understand what is happening over here. Say we have 2 threads. When both the threads are executing the getInstance method at the very same time, they will both check that the instance underscore DCL variable is null on the very first execution. So both the threads will come to line number 10, but only one thread will get access to this monitor. Say thread number 1 gets access to this monitor and it checks again if the instance underscore DCL is null. Thread number 1 will find this as null, so it will create a new object of double check locking initialization class, initialize it to instance underscore DCL, and return the same. Once thread 1 releases the lock, thread 2 will come and again check whether the instance underscore DCL is null. Since the previous thread has already created this instance, thread 2 will see that this is not null and it will not go ahead and create the instance a second time. It will return the instance that was created by the first thread. So this extra null check is helping us realize that the first thread has already created the object and any subsequent threads who wants the lock need not to create the object again. So this is a good example of double check locking. Even though double check locking looks completely thread safe, on a very rare occasion, it might fail and break the singleton pattern due to a concept called partial variable initialization. To know more about partial variable initialization, I have left a link in the description below. To overcome the partial variable initialization failure, we can add a volatile keyword in the instance variable declaration. Now, what is a volatile keyword? When two or more threads are working on a class, and if two threads are running on different processors, each thread will have its own local copy of the instance variable, such that when one thread updates its local copy, the same should be reflected throughout all the instances of that object. This is done by the volatile keyword, and it helps maintain data consistency. Even though we have come up with a good initialization technique for a singleton class which is completely thread safe, remember that using synchronized keyword in your code makes the code a lot slower because it actually creates a monitor and blocks all other threads that want to use that particular monitor, and it is available for only one thread at a time. So that is why Pugh came up with a very unique approach to singleton initialization. We call it the Pugh singleton initialization. With Pugh's approach, we have to create an inner holder class which will create the instance of the outer singleton class in an eager fashion. But the inner holder class will be called via the outer getInstance method of the singleton class. Thus, even though it looks like an eager initialization, but it forms a unique case of lazy initialization as the instance is only created when we call the getInstance method. Also, since the instance underscore BP is static and final, there is only one unique unmodifiable copy in memory. This approach is completely thread safe and does not require any synchronization. This is the most sought after approach for singleton pattern. Let's test this approach in the main method. At first, we'll test this approach in a single threaded environment and then we'll go ahead in a multi-threaded environment. Let's execute this main method to see how it is working. You will see both the object, both the Pugh initialization.getInstance call are returning the same object instance. And no matter how many times we call it, it will always return the same instance. Now, let's execute it in a multi-threaded environment and see how it goes. Even in a multi-thread environment, you will see it is returning the same object instance. No matter how many times you run it, it will always return the same object instance. So this is the most perfect example of singleton initialization without synchronization, and it is also considered the most efficient. Now, we will look into a few ways in which we can violate the singleton pattern. There are basically three ways in which we can violate the singleton pattern. Number one is using reflection, number two is with cloning, and number three is with serialization. We will start with reflection. One of the features of Java reflection is that we can change the access modifier of any variable, method or constructor to public from a more restricted form like private or protected. This sounds very disruptive for singleton pattern, as if we were able to convert the private constructor to public, we can freely create as many separate instances of the class as we want. This would directly violate the singleton principle. To resolve this issue, we will add some code inside the private constructor declaration rather than keeping it empty. At first, we'll put our theory to test whether reflection can be used to violate the singleton pattern. Over here, we have created a class called Singleton Reflection Violation, which is a lazy implementation of the singleton pattern. Inside the main method, at first we have called the singleton reflection violation.getInstance method twice to see whether the singleton pattern is violated before using reflection. Then we have used reflection to convert the private constructor of this class to public, and then we have called the constructor.newInstance method to create new instances of the singleton reflection violation class. So basically in this section we are trying to create new instances of this class using reflection. Let's see how it goes. Here we see that before using reflection, the singleton reflection violation.getInstance was returning the same object instance. But after reflection, they are returning different object instances. So this means with reflection, we can violate the singleton principle. To resolve this issue, we will use the private constructor in the singleton class initialization. If you see here, inside the private constructor, we are checking that if the instance variable is not equal to null, then we are throwing the exception. Now, why are we providing this check? Think that when this getInstance method is called, it is calling the new singleton reflection violation fix constructor to create an object. If this instance variable is null, then it has to go ahead and create an object. So a call to this constructor for a very first time should not throw any exception. So that is why we have put if instance singleton violation fix not equal to null. That means that the instance has been populated for at least once. Then it will go ahead and throw a new instantiation exception, which gives a message that cannot create instance of a singleton class using constructor, use getInstance static method. In this way, we can notify the user who is using reflection to call this constructor that an instance is already in place and it cannot be done using a new operator. Now, let's run the main method of this singleton reflection violation fix to see whether this exception is being thrown if we are using reflection or not. So in this main method, we are at first calling the singleton reflection violation fix.getInstance method twice to see how the singleton pattern behaves before reflection. Then we are going ahead and making the constructor as public, and then we are calling the new instance method of this constructor, which will actually replicate the new operator. Let's see how it goes. So if you see over here, for the very first time, the two calls gave the same object instance. So that means the singleton principle was holding good. After that, when we tried to call the constructor using the new instance method, it threw an exception. It threw an invocation target exception saying that cannot create instance of singleton class using constructor, use the getInstance method. So this is basically the exception, that is the instantiation exception that we raised from our private constructor. So basically in this way we can stop anyone from using reflection to violate the singleton principle. Now we will see how to use cloning to violate the singleton pattern. We'll also see a solution on how to stop that. Using cloning, you can clone an already created singleton object into a new object. So basically, by implementing the clonable interface and overriding the clone method, we can allow any singleton object to be cloned. This directly violates the singleton principle. Let's go to the code to see how this violation is occurring. In a singleton initialization class done with lazy technique called singleton clone violation, we have implemented the clonable interface and we have overridden the clone method from the object class and return the super.clone. So basically this will perform a shallow copy of the parent object. If we execute this method in the singleton clone violation main, we'll see that in the first section where we are calling the singleton clone violation.getInstance twice, it will give the same object reference, but after we perform the clone operation on the first two objects and initialize it to two different objects and print those objects, it will give different object instantiation, thus violating the singleton pattern. Let's execute this method. So over here, if you see, the first two clone Singleton clone validation.get instance call, it returns the same object instance, whereas after cloning, the same object instance returns two different object instances. That is because the clone operation is creating a copy of these objects into a new object, which directly violates the singleton principle. Now, how to resolve this issue? We have created one more class called Singleton Clone Violation Fix, implementing the clonable interface. But this time, in the overridden clone method, we are throwing an exception called clone not supported exception with the message cannot clone instance of a singleton class using the clone method. Use the getInstance static method. This time, when we are calling the clone method from the main class, it will directly throw this exception, that is a clone not supported exception, with this message. Thus, it will not allow the end user to perform a clone operation on this singleton object, thus fixing the problem. Let's execute the main method and see how it goes. If you see over here, the first two call to the singleton violation fix.get instance returns the same object instance, which is correct. But once we start calling the clone method and print the object, we will get cannot clone instance of singleton class using clone method. Use the getInstance static method, which is the correct notification for this kind of situation. This will not allow the end user to clone the singleton object, thus fixing the violation. The last way to perform a singleton pattern violation is by using serialization and deserialization. Using serialization, you can serialize an object and then perform deserialization on the same to create a new object. So by implementing the serializable interface, we can use any singleton object and create a new object out of it. This directly violates the singleton principle. Let's see how this is done and how we can resolve it. So we have created a class called Singleton Serialization Violation, which is implementing the serializable interface. Now, by only implementing the serializable marker interface, we will give the authority to this class to allow serialization and deserialization on this class. In the main method, we at first call the singleton serialization violation.getInstance method twice to see whether the singleton upholds before serialization. How we perform serialization is we create an object output stream, and inside the constructor we pass the file output stream and give a file name. Over here we have provided object1.ser and object2.ser for the two serialization objects singleton sv1 object1 and singleton sv object2. So in this way we have created a serialization of these objects, and then we deserialize the same object in using object input stream, and we pass on the file name object1.ser and object2.ser. Okay. After deserialization, we'll just perform the instream1.read object and instream2.read object, which will actually read the deserialized objects and give us the object value. We'll see whether the object value after serialization remains the same or not. Let's run this program. If you see over here, before serialization, the object value remained the same. That is, it was not violating the singleton principle. But after serialization, as per the concept, it will create new objects after deserialization. Over here, if you see, after deserialization, they are creating two separate objects, thus violating the singleton principle. How to resolve this issue is we'll create a new class called Singleton Serialization Violation Fix, implement the serializable interface with a twist that we'll also write a read resolve method, a private method returning an object type, and return the instance of the singleton class. Okay. So what this basically will do is while deserializing, JVM usually calls this read resolve method to replace the object in the in stream. This is where we are returning the object created by the singleton class for the very first time to let JVM know not to create new objects for during deserialization, but to return the same singleton object. Let's execute this code. In the singleton serialization violation fix main method, we are performing the same serialization and deserialization of the object we have created first, and we are printing the object. But this time we will see that the objects in 3 and 4 will return the same value as in objects 1 and 2, because in the read resolve method we are returning the same object that has been created for the very first time. Let's execute this method. And our expectation is correct. For the very first time, it has returned two objects of the same instance, and after serialization as well, both the objects are still the same. Thus, we are able to resolve the violation using read resolve method. So, to summarize what we have learned so far, few of the best practices to create a singleton class is number one, to use build Pugh initialization to create the singleton class, because this is the best and the most efficient way to implement a singleton pattern. Number two is avoid reflection. Even if you're using reflection, make sure that you add an exception to this private constructor such that any external agent cannot use reflection to create an object of this class. Third is to avoid implementing serializable interface on a singleton class. And number four is avoid using implement clonable on a singleton class. So these are the best practices you should follow while creating a singleton class. I will be attaching all the necessary links required in the description below. If you like this video, please like and subscribe my channel, because going forward I'll be uploading more and more videos on various design patterns and software architectures. Thank you.